Hey physics friends, I'm here with another page from the Fluids Workbook for AP Physics 1. This one's called Oscillating Cube. Dun dun dun. This is why we're doing this at the end of work conservation of energy and simple harmonic motion. Let's talk about this. So the first thing I want to point out, right, is that this cube is at rest when it is halfway submerged in the water, right? So we walk up on it, we see, oh, it's floating. It is exactly halfway in the water, half out of the water, right? And so if we're floating here in equilibrium, it's at this point where the buoyant force and the gravitational force will be equal, which is not what it asks for in part A. In part A, Carlos has fully submerged the cube, and then he lets it go. So because our buoyant force is related to the volume of the fluid displaced, like if the equilibrium case is when half of the cube's volume, right, is displacing liquid, if we fully displace the liquid, right, in the shape of a cube, then that means the buoyant force is going to be larger, which means this cube is going to accelerate upwards. Okay, so, all right, we are now supposed to derive an expression for the net force while it's in this fully submerged position. If it says derive, you should start with something on the formula chart. So I guess sigma F is equal to MA is a good place to start, even though we actually aren't asked for the magnitude of the acceleration. We are just asked for essentially the left-hand side of this Newton's second law expression. And so there are two forces that are acting on the cube, right? And so when we expand those, thinking about what we just did with like the volume there, we should get rho s cubed, because that's the full weight of the water in the cube that is displaced multiplied by g, so the weight of the water displaced, minus mg, which is the weight of the cube itself. So weight of the water displaced minus weight of the cube. We actually want to investigate what's going on when the cube is not fully submerged. So if, all right, we are only partially submerged, like how is this equation then going to change? So our buoyant force equation there, right, length times width times height, right, of the water that is displaced. Well, I would say the length and the width of the cube, like that's the part that's getting dunked in. It's like the face of the cube. But h is going to vary. So I could say length and width, well, that's going to be s squared. But depth, I think, is a better word than like height, right? So it depends on how deep we are pushing the cube into the water. So I did this because I knew in the next part, we want to make a graph. So I just pulled that equation that we just thought about, the one for the partially submerged cube, right? And so looking at this equation, looking at the graph axes that they've suggested for us, net force is on our y-axis, height submerged, or perhaps you could say depth, is on our x-axis. This equation that we just wrote fits into y is equal to mx plus b. So actually, we know that this function is linear. Okay, well, let's get some like ordered pairs in so we can draw this line. An easy point to consider would be when x is equal to 0, as in what happens when the box is like not in the water. So if it is just in the air and Carlos lets go, then the net force acting on the box is going to be mg downwards. So we're going to use the convention that, you know, down is negative, up is positive. So I have a y-intercept, or a net force intercept, right? When x is 0, my net force should be mg downwards. I also know, right, from the very first part, you could almost like blink and you miss it. I know that when the cube is sitting halfway submerged, that's going to be its equilibrium point. So when the water level is halfway up its side, right, that is where my horizontal intercept would be. Okay, so where my net force is 0, my x value is half of s. And, right, we established that it was a line. right? We also know that since the buoyant force is based on the amount of fluid displaced, once this cube is fully in the water, then, well, we've kind of hit the cap on how much water we can displace. So if we go deeper than height S, which makes this graph label kind of weird, let's adjust that, shall we? Let's say X is going to be the height of the bottom of the cube below the water. So let me kind of clarify what I mean by that. Okay, so I've labeled these regions here with essentially where the cube is and the net force that the cube is experiencing. So if it's above the water, it experiences negative mg. As the net force, if it's mostly above the water, it experiences a net downward force, right? If it's, I said that backwards. If it's mostly above the water, it experiences a downward force. If it is mostly below the water, it's going to experience an upwards force because that net force is positive, right? And then once it is entirely submerged, the force, right, becomes that constant value, the one that we drew our free body diagram for, right? That rho s cubed g minus mg, right? Once we are fully in. Whew. So all of that work to now answer whether or not Carlos is correct about the cube being simple harmonic motion. Well, it's definitely not simple harmonic motion when it's in the air or when it's fully submerged, right? Because the force is constant. One of the primary properties of a simple harmonic oscillator is the presence of a restoring force, right? And the restoring force has two characteristics. It's got to be proportional to how far away the object is from its equilibrium position. So like if it's twice as far away, the restoring force should double, right? If it's 3 times as far away, the restoring force should triple, right? And that restoring force always needs to point back to that center equilibrium point, right? So looking at our graph, well, it is linear, right? So that's going to take care of like the direct relationship between the restoring force and the displacement from equilibrium. And the direction is also correct, right? Because when we're half submerged, right, then the net force is downwards, like it wants to pull us down to like that center point, right? When we are mostly submerged, right, our net force is going to be upwards because our buoyant force is going to be bigger, right? So then our net force, we're trying to bob back up so that we are only halfway submerged. So yeah, I mean, that works, right? Both requirements are fulfilled. So as weird as it is, this little bobbing cube does exhibit simple harmonic motion behavior.